Hello and welcome once again to the Maths Jedi channel. This is another video in the A-level series. Moving on to logarithms. If you're new to the channel, please do drop a like or subscribe. That would really help out the channel a ton. Just in case you're new to the channel, these videos really are for people who are working through the A-level syllabus, just replacing the lessons that you probably would have had at school. As I said, please do leave a like if you're a first timer. That would really help me out. This is a topic that's completely new, so you've not done this before, but you have done related topics at GCSE, and I'll try and link those up as I go through. So logarithms is all to do with powers, and first of all, if you're looking at a problem such as this, finding p where p cubed is 343, well, you should have done that or learnt that at GCSE. Hopefully you do know that that is in fact 7. And so what you're focused on there is just understanding that 7 cubed makes 343. However, let's just flip this problem a little bit on its head. Let's have a look at this. Let's say we were looking at a power of 3. A power of 3 that makes 343. What power of 3 makes 343? Well, the only way you know to do that at GCSE is to do it by trial and improvement. So just trying different things out, trying to find values for which that works, and then understanding what that power might be. It takes you quite a long while to do it. Now, what logarithms enable you to do is to shortcut that process. So to explain what logarithms are, we're then focusing in on a particular issue, this particular issue. So to avoid using trial and improvement, we need to define what we're looking for. So here in this example, we were looking for a power, particular power, with a base. In this case, it was 3, and we wanted to understand how far to raise that number, that 3, to get me an outcome. In this case, it was x, 343. Now we can define that as a logarithm. That's what we define these things as, a logarithm. So y is the logarithm. Y is equal to the logarithm to the base a of x. The best way of thinking about that is that these two things are interchangeable. So if you think back to the previous page, we had 3 to the power of something makes 343. So the base was 3. So that's why the base of the logarithm is 3. 343 was the outcome. 343 goes here. And we were looking for this mystery power, and this mystery power goes at the front in a logarithm. So to enable us to find out what that mystery power was, to avoid using trial and improvement, we established the idea of that being called a logarithm. So, for example, we know that 2 to the power 5 is 32. In this case, 2 is the base, 32 is the outcome, and 5 is the power. So, 5 is the logarithm base 2 of 32. Base was 2, the base is 2, 5 was the power, so 2 raised to the 5, and then 32 was the outcome, so 32 here the outcome. So why are logarithms important? Logarithms are important because you can apply them to the same situations as you dealt with at GCSE. Now at GCSE we dealt with powers in quite a few different ways, but one of the most fundamental ways we dealt with things with powers was in the rules of indices. And just like you have rules of indices, we do have rules of logarithms. We call them the logarithmic laws, or the laws of logarithms. And they're very similar to the rules of indices. They're just interchangeable formats. Let's look at those. So when we're studying indices, we found the following important results. For example, we knew that anything to the power of 1 is itself. Now in this case, a is the base, a is also the outcome, and 1 is the power. And that must mean that in logarithmic form, the log of a base a of the same outcome must be 1. This and this are the same, but written in two different forms. What other rules did we learn? We learned that a to the power of 0 is 1. Anything to the power of 0 is 1. So again, a is the base. The outcome this time is 1, but the power was 0. In logarithmic form, the log of 1 to any base actually is 0. The log of any base of 1 is 0. Again, this and this are interchangeable. When When we learned about indices, we learned about the multiplication law. We learned that when you were multiplying things that had the same base, you could add the indices. Well, this is an interchangeable format of that. So let's look at this. So let's take a logarithmic expression. Say this is the power in this case. So a to the power of m is x and a to the power of n is y. So a to some power is x and a to the power of a to another power is y. So look at those. These are the logarithmic expressions that apply those. We know from the rules of indices that if you multiply these two things together, you can add the indices. So a to the power of m plus n. So in logarithmic terms, we know that m plus n is the power, a was the base, and xy was the outcome. M and n is the power, a was the base, xy is the outcome. This and this are interchangeable. But we also know that in this situation, the m was this logarithmic expression and the n was this logarithmic expression. So we can actually substitute this m as that logarithmic expression and this n as that logarithmic expression. So notice what's happening. We've got xy here in the brackets and we've got log x and log y. This is the same indices rule. We said in indices, if you multiply things with the same base, you could add the indices. And here we've got the multiplication of two outcomes, and actually what we're doing is we're adding the indices. We're adding the powers together. Division just the same. In indices, we met the idea that if you subtracted two things with the same base, you could subtract the indices. So m minus n in this case. Again, a is the base, m minus n is the power, x over y is the outcome. So in logarithmic term, we have the logarithmic format. Logarithm of x over y is m minus n. In a similar way to before, we can substitute m and n, and that gives us this expression when we have two logarithmic expressions being subtracted. Again, this is just this rule, just rewritten differently. So two things divided, you subtract the powers. Two things divided of the same base, that's what this is saying. Two things divided of the same base, you subtract the powers. That's all this is saying. It's just in a slightly different format. At GCSE, we also learned about the power rule. With indices, if you had things in brackets like this, you would multiply these two indices out. So we knew that. In this case again, because we've got x to the power n as an expression, we can rewrite that as mn is the power, a is the base, x to the n is the outcome. And then just like before, we know that m is log a of x, because we wrote that up here. So we've got n lots of log a of x is log a x to the n. Again, this is the same thing. You're multiplying things together, and you would then multiply the powers together. So if you're multiplying things together, you multiply the powers together. So when you multiply things together, that's what this is doing. You multiply the powers together, that's what this is doing. Now in short, that's quite interesting. We call this sometimes bringing down the power. So it's a bit similar to differentiation, but it shouldn't be thought of as differentiation. It isn't the same. What you are effectively doing is just distributing out the rules of indices in a different way. But we do talk about sometimes bringing down this n. So log base a of x to the power n, you can think about n as coming to the front of that expression. That's effectively what's happening here. It's a bit like differentiation, but not the same. Now, you'll meet two bases with logarithms that you'll use often, and those two logarithmic bases are on your calculator. So if you look on your calculator, you will see the log button, the log button, and the ln button, the natural logarithmic button. So those two buttons are very important for logarithmic calculations because you'll be using those pretty commonly throughout your work. So the log button and the ln button, the natural logarithmic button. Those two buttons are on your calculator. Have a look to where they are. We'll use them today, but just be aware that those are the buttons that you'll be using quite a lot with logarithmic expressions. Now, we sometimes come across problems, and common problems can include different variants. So I'll talk about some of the different problems that you can have. So we'll talk a little bit about changing the base first of all. So let's look at this expression. This is saying that the base of this logarithm is 5 and we're having the outcome as 8. So what it's asking you to do is to calculate the value of log base 5 of 8. In other words, 5 raised to some power is 8. What is that power? So let's have a look at that. Now, if we say that that power we're looking for is x, in other words, 5 raised to the x is 8, we're going to use the rules of logs to help us. So there's 5 to the power of x equals 8. That's just this expression rewritten. What we're going to do is we're going to say take logs on both sides. That's what this is called. It's called taking logs on both sides. So the log of 5 to the power of x is equal to the log of 8. Notice how we're using the log expression here, log base 10 on both sides. It doesn't matter what logarithmic base you use as long as it's the same. Because we've got a log button on our calculator, we can use that quite easily. So log base 10, 5 to the power of x equals log base 10 to the power of 8. We just write log, we know we mean log base 10. Now, that earlier rule about multiplying things together and bringing down the power, effectively I've got that happening here, so x log 5. And we want x on its own. This means x multiplied by log 5. So if I want x on its own, I need to divide by this log 5. So log 8 divided by log 5 should give me the answer. And if you do that on your calculator, you will get 1.29 to 3 significant figures. So log 8 divided by log 5. Let's just have a look at that, make sure you've got that understood. So I'll show you the buttons on the calculator and I'll take you through the basic expressions. So here is my calculator. Let's have a look at the buttons that we need to use. So here are the log button and here's the ln button. And you can see above it, it says 10 to the power of something and e to the power of something. Those are the inverses. We'll come to those later on. But the log button and the ln button are there. What we were doing in this calculation, if you remember, is we were doing log to the base 10 in both of those calculations. So let's just have a look at that again. So in this particular example, we were doing log 8 divided by log 5. So log 8 divided by log 5. So we're going to do log of base 10 and then divide by log base 10 of 5. 1.29 as I said. So that's the number you get. So that's a good overview of how you use logarithmic buttons on the calculator. What other types of problems could you get? So you could have problems that involve you solving equations. And if you're solving equations, it's important to make sure that you understand the rules of logarithms apply as much as possible and try to use them as much as possible. Let's have a look at a couple of examples. Here's one. So it's asking us to solve this problem here. Solve log 5x plus 2 equals log 5 10. So both logs here are base 5. Now the first problem with this is that you've got two things that are in a base of 5, but this one, this number in the middle, is not in base 5. So one of the first most important things you've got to do is change this 2 into a format that's base 5. So how do we do that? Well, it's important to make sure first of all that we're getting everything in the same base. So we can put things into the same base if we're careful. For example, you can multiply 2 by a logarithmic expression. But what logarithmic expression multiplied by 2 makes 2? That's what this is looking at. What's happening here is that you're multiplying 2 by log base 5 of 5. That's because we know from earlier that log base 5 of 5 is 1. We know 5 to the power of 1 is 5. And so this does not change the equation. However, this is something we know because look, it's 2 multiplied by log base 5 of 5. So we know from the rules of logarithms from earlier, this is the same thing as log to the base 5 of 5 squared. So you're bringing up the power here, doing the opposite thing to what we did earlier. We know 5 squared is 25. So log base 5 of 25. We know 5 squared is 25. So we can write log base 5 of x plus log base 5 of 25, we know that's 2, equals log base 5 of 10. So now it's written all in the same format, everything with bases of 5. Now that we've done that, we can use the rules of logs. Because look, there's two logarithms being added here, and the laws of logarithms said that when you've got two logarithms being added, you can multiply the outcomes. So 25x in this case. And now that we've got things in the same base, you can almost anti-log everything. Just look at the outcomes and look at them in isolation. So 25x equals 10, because you've taken the logs away on both sides, you've anti-logged everything. It must mean these are the same. So if 25x is 10, x is 10 over 25, or 0.4. Here's another problem. If it's asking you to find x to 3 significant figures, and we've got 5 to the power of 2x equals 30, well, we've got a log base 5 again, and we've got log 30 here, but this time we're going to try and do things a bit differently. So we're going to take logs on both sides, a bit like we did earlier. So again, this is base 10 logs we're using here. And so we're going to take logs on this side, logs on that side. We've got a 5 raised to the power. So as with earlier, we can bring down that power. So 2x log 5 equals log 30. And then because we've got logarithmic expressions, let's divide by log 5. That gives us an expression in x and an expression in logs over here. We can use the calculator to calculate what this is. So log 30 divided by log 5. And then we can divide by 2 to get x on its own. Using a calculator, you'll get the answer 1.06. Very simple. Lastly, an example such as this, we've got two different bases this time, but that doesn't matter. We can still take logs as normal, in this case logs base 10. So we've got log of 4 to the power of 3x plus 1, log base 10 of 7 to the power of x plus 2. Again, you can bring down the powers, 3x plus 1 and x plus 2. We can use the rules of logs, so the distributive law in this case, so we're multiplying everything by log 4 on this side, and multiplying everything by log 7 on this side. So 3x log 4 plus log 4, because that's 1 times log 4 and 3x times log 4 and x times log 7 and 2 times log 7. So we've just distributed out. And again, using the rules of logs, we can bring things together that are alike. So try and bring all the x expressions on one side and all the things that aren't x expressions on the other side. So look, we've got two expressions here, both of which have got logarithmic expressions in, and so we can divide by 3 log 4 minus log 7 to get x in isolation. So we'll do that. And so we use the calculator to work this out, again base 10 all the way through, and if you're careful with your calculator, you should get 1.13. This is a very advanced example of a problem. Okay, let's have a look at some questions now. We'll go into the book and have a look at some things, make sure we've got a good understanding about what's going on, and then I'll leave you time to have a go. So here is exercise 14D, and make sure we understand what's happening here. Fundamentally, one of the things we've got to recognise is what kind of problem we've got. It's on page 320 in the textbook if you want to follow along. So just have a look and see if you can find that first of all, and then we'll crack on and have a look. So I need to pull up my answer sheet here so I can write and annotate. So I'll do that over here. Right, so first of all, let's have a look at a couple of these problems. So rewrite using a logarithm. So we're going to do a couple of these. So we'll do E here just because it's the hardest one. So if I get my pen, I can show you how this operates. So first of all, let's have a look at this one. We've got a base 0.2, a power 3, an outcome 0.08. So this is very easy. So this is going to be log base 0.2. The outcome was 0.08. And the power was 3. So this is just another form of this. Again, going the other way, we've got part C here. We've got the base of 9. We've got the outcome is 3 and the power was a half. So 9 raised to the half is 3. We know that, of course. They're very easy examples to start with. Let's have a look at some of the others. Okay, so here's an example of some of the others. We're going to look at these. So some of these we'll do without a calculator, so we'll understand what's going on. So let's have a look at this one first of all. So we can understand and use these ones. So B, for example, so we've got a base of 5, an outcome of 25. 5 raised to what power makes 25? Well, we know that's 5 squared, so we know this one is 2. So 3b is 2. Similarly over here, we've got log of base a. The outcome is a to the power of 10. So a to what power makes a to the power of 10? Well, it's just 10. So we know that's going to be 10. And similarly, let's do one other. 4 raised to a power makes 0.25. So let's think about that. So 4 raised to what power makes 0.25? So 4 to the power of x equals a quarter in this case. So what's going on with this? So x has got to be minus 1. So this is going to be minus 1. So you can see those rules of logarithms and those rules of indices, they're definitely linked together, and you can think through some of these problems really easily. Let's look at some of the harder ones. Let's go into here. So I'll look at f, which is quite a hard example. So we've got a base of x raised to the power 2. So base of x raised to the power 2 is 2x. So what's happening here? We need to find out a value of x. So x squared equals 2x. So how would I solve that? Well, you can take the 2x over the other side. We can take out x as common. That gives us two answers. X is 0 or x is 2. So you can see, by using the rules of logarithms, you can start to understand how problems such as this can be dealt with. It's really quite easy to do. I'll leave you to do the others in that exercise. They're really quite straightforward to do. Work your way through those, and hopefully you'll crack through those quite quickly. 14e, page 323. Let's look at a couple of those. We're going to make sure we go through some of these, make sure you understand it a little bit. We're going to write these things as single logarithms. I'm going to take some hard examples of each one, but I'll leave you time to do some of the others so you've had an opportunity to practice. So let's go through and have a look at this one first of all. It's asking us to write it as a single logarithm. So let's have a look and see if we can use those rules of logs, those laws of logarithms to help us. So here's an interesting problem here. We've got base 10 being used. So log base 10 of 5, log base 10 of 6, and log base 10 of a quarter. These two things are added up. These two things are subtracted. So we can think about using rules that we would normally do. So over here, we're going to do the rules of logs, first of all, on the multiplying bit. So this is two logarithms being added. So we know that when you're adding up two powers, that's when you're multiplying things of the same base together. So I can write this as log to the base 10 of 30, because 5 sixths are 30. So these two things were being added, so we can multiply the outcomes. And again, you've got two logarithms being subtracted here. So that's the same thing as when you are when you're subtracting two logarithms, we can divide them. So we can think about 30 divided by a quarter. That's the same thing as multiplying 30 by 4. So that's log of base 10 of 120. So that's now writing it as a single logarithm. Let's check our answers, make sure we're right. So 14e. Here's 14e. We had log base 10 of 120. Let's just trash the annotation because it's getting in the way. We're going to look at our question here. We were doing, what number were we doing? We were doing this one, 1e. So let's have a look at 1e. And you can see they're getting log base 10 of 5, log base 10 of 6. They do exactly the same as me. They're multiplying it first of all, and then they're getting log base 10 of 120. Very straightforward. So we'll look at a few other examples. Let's look at this one down here. So log base a of square root a to the x, we need to write it in terms of log base ax, log a base of y, and log base az. So we're going to do this one here. So what's this saying? So this is saying a to the power of something is is going to be this outcome, but we're looking for rules of logs here being used. So first of all, we're thinking about, well, this is log base a of a to the x to the power of a half, first of all. So let's deal with the square root first of all. We know from the rules of logarithms that I can bring the power down, so half log a power is ax, and then because I've got two things being multiplied here, I can use the rules of logs to write that out separately. So I've got log base a of a plus a half lot of log base a of x, okay? But then we know that log base a of a is 1, so that effectively is a half. So we've got a half plus a half log base a of x. Let's check our answer. 3 part E. And there it is, half plus a half log a of x. So you can see rules of logs are quite tricky, but if you're thinking about the laws of logarithms and the laws of indices as being interchangeable, it's really helpful to do that. Very much helpful to do that and work your way through. Let's look at a couple of other examples. So question 4, we'll look at 4a first of all. This one has got base 2, so we're looking at base 2 problem. So on the left hand side we've got two logarithms being added, so we can think about this as being through the law we had first of all with the two logarithms being added. Again, you're adding the powers here, so you can multiply the outcomes, so 3x here. So we've got log base 2 of 3x is equal to 2. So again, rewriting that into a power form, we've got a base 2, so 2 to this power, 2 squared is 3x, that was the outcome. And so we know that 4 is equal to 3x, so x is 4 over 3. Very easy. A more difficult example, D. These are base 9 expressions, so we can move everything with base 9 onto the same side, so I'll do that first of all. So 2 log 9 x plus 1 minus 2 log 9 of 2x minus 3 is equal to 1. These 2's in front, we can raise them up in the same way as we've done in previous questions. So log 9 x plus 1 all squared minus log 9 of 2x minus 3 all squared equals 1. Sorry, it's all squared. Just need to change that. Now, these two things are logarithmic expressions being subtracted, so we can divide the outcomes using the rules of logs. Because both things are squared, we're going then to look at this expression here. Because both things are squared, that's effectively squaring the top and squaring the bottom. So I can write that as one lump. Let's make that bracket a bit better. And then using the rules of logs, that's the base, that's the power. So 9 to the power of 1 equals x plus 1 over 2x minus 3, and that's all squared. We can square root both sides, so that's going to be 9, so square root of 9 is 3. And then I can multiply at the bottom here, so 3 lots of 2x minus 3. Make some space for myself. And that's going to be 6x minus 9 equals x plus 1. And then taking the x's together, you end up with x being 2. Let's just check our answer, make sure we're right. What's that? 4 part D. Oh, it's here, yeah. So 2 log 9, yep. So all the same through. X is 2, easy. Okay, so again, not as straightforward, but certainly doable. And I'll encourage you to do the rest of that exercise and then work your way through those. That's it for today's lesson. So make sure you've taken your way through those and make sure you take account of all that because that's quite important for you to do. And we'll look at exponential equations next time. Thanks very much for watching and see you soon. Bye bye.